for Germany. Thank you. And the co-director of the Center for AI and Data Science, his background in science and mathematics. He obtained his PhD in Germany, did a postdoc at ETH Zurich, then got $1.8 million from the Swiss National Science Foundation, and they gave him a professorship. And then after that, he went to Germany, and now he's in this beautiful place in Bavaria, University of Würzburg. And in 2014, he was awarded a junior fellowship from the German Informatics Society. I met Ingo in 2017, just after I joined here. And at the time, I had a student, his name is Tim Larotte, who graduated from the Network Science Institute. And he had never been to Europe. And he found Ingo's work very interesting. And he came to me and said, Tina, would you send me to Ingo's lab for the summer so I can spend my time in Zurich and also do some research with Ingo? And Ingo was very kind and said, absolutely, send Tim over. And Tim had a brilliant time there that led to papers. He grew intellectually there under Ingo's stewardship, and I'm forever grateful for that. So thanks so much for coming.
Yeah, thank you so much, Tina, for this very kind introduction, and also for the hospitality here. So I'm really flabbergasted. It's great to be back. I can't believe that it's been 8 years since I've been here last time. I also looked at my slides from back then, just to see what I talked about back then. And it's also a great way to reflect what has happened in 8 years. And yeah, I'm very happy to be able to give you an update here. And also it's great to see some familiar faces in the audience. Okay, today I want to talk a little bit about our work on machine learning for temporal graphs, specifically about some more recent works in which we consider what we call, and I will explain this later, causality-aware graph neural networks for time series data and some approaches to study their expressivity. Okay, so I guess as we say in German, I mean, first of all, let me introduce the team. You see here some brilliant PhD students as well that have been instrumental in this work. Specifically for this talk, this would be Franziska Heek here on the left and Lisi Chakajia, who were actually leading some of the works that I'm presenting here today. I guess in German we say bringing alts to Athens when I talk about the importance of network models of complex systems. But this also serves to illustrate some of the areas in which we apply them. So we have projects where we apply graph models for single cell biology data, for social networks, specifically collaboration networks and software engineering teams, but also in the modeling of, for instance, large-scale infrastructure spatial networks. Okay, so that means the idea is that we can use graph or network models with nodes and links as some kind of a universal mathematical abstraction for these systems that consist of many interacting elements. Now, the question that we can ask, and I would like to give a little introduction to this so that we are all on the same page, and you can see how this links to the stuff on temporal graph neural networks that we have done later. How can we apply end-to-end deep learning approaches to such network data, to data with a graph structure? Well, first of all, how can we apply deep learning to other data? Well, this is based on a simple model that is called a perceptron, which is essentially a linear classifier that is loosely inspired by the structure of a neuron. So if you make a mathematical model, we basically have some inputs that we aggregate with some learnable weights, and then we create a linear combination, apply a nonlinear activation function that gives us a decision boundary. Such a simple model is just a linear model, so it means we have a linear decision boundary, and in fact, it is exactly equivalent to a logistic regression model if we use a sigmoid activation function. Now, something interesting happens if we combine multiple of these perceptrons to what we call a feed-forward neural network. So that means we have a network of these perceptrons with some input and a hidden layer. So that means we have these inputs that feed into these perceptrons, and then the output of the perceptrons is again aggregated in another perceptron. And the interesting thing that happens is that now we can model also nonlinear decision boundaries with arbitrary complexity. This is essentially what is the statement of what is called the universal approximation theorem. Okay, now the question is, how can we apply this to graph structured data? The problem with this approach is that across layers, these neurons or the perceptrons are fully connected typically. And the idea of applying them to graph structured data is now that we can use the network topology to propagate features of the nodes. How does this work? We do something in many graph neural networks that is called neural message passing, where we essentially use the graph topology to iteratively update features that we assign to the nodes. Either we can assign them artificially, or we have some natural node features in the data that we can use for that. Essentially what we do is we consider a discrete time dynamical system where this HIT denotes the features of a node I at time t. And then, for instance, here for this little example graph, we could assign at some t equals 0 initially some features. We can just enumerate the nodes if you like, 1, 2, 3, 4, 5. And then we update the features after every round of this message passing according to some simple rules, like, for instance, here, this simple neighbor-based aggregation rule. So it means we apply a function where we have some learnable weights, and we can also apply some nonlinear activation function. Here, to keep things simple, we make a very trivial approach where the weights are just all ones, and the linear activation function is just a rectified linear unit, which means basically we can neglect it. So it means this is just a neighbor aggregation. So now after one round of message passing, we get updated features. After another round, we get, again, updated features. And there's a couple of things that you can already see with this simple dynamics. First of all, we have different features depending on the position of the nodes in the graph. And the second thing that's not so nice is that the features start to explode. This is easy to understand because if we just apply this aggregation, with every round, we are changing the scale of the features based on the leading eigenvalue of the adjacency matrix. So what we can do is we can apply some normalization in the aggregation step. One approach that we can do is what we call symmetric degree-based normalization according to this rule here. And this is essentially the basis of what we call a graph convolutional network. So what this essentially does is we are doing a diffusion of the features because of this normalization, which we can also express based on a normalized graph Laplacian, which can be given in this form. So essentially, we are smoothing the features of the nodes over time throughout the graph. And then you see if we apply this rule with the normalization, then we first of all get features that always sum to the same value because we have a conserved quantity now. And also, again, the features capture uniquely the position of the nodes in the graph. And we kind of capture the symmetries of the graph in terms of the features. So you see all of these nodes, the two nodes here, they are kind of equivalent because there's the symmetry in the graph. The center node has a different representation and the other nodes on the other side as well. Okay, so that is the basic idea of applying end-to-end deep learning to complex networks. If we sum this up, then we have a neural network architecture for graph structured data. So that means given a graph, we have this message passing layers, which we can see as a computational graph, as a neural network, where the perceptrons are now connected based on the graph topology. Depending, the number of layers now depends on the number of rounds of message passing that we do. So then we have, again, this differentiable function with some learnable parameters. We have this neighbor aggregation, and we have a nonlinear activation function. And then what we can do, for instance, in a supervised setting, is we can always compare the output of the model with some ground truth that we have. And then we apply a differentiable loss function, and then we can calculate the partial derivatives with respect to this loss function, propagate them back through the model, and by this actually learn the weights. And the cool thing is that what we do with this is we are learning what we could say a useful vector space representation of the graph. Useful in the sense that it's actually useful for the task that we trained it on. And this is also what we mean by end-to-end, that the representation that we learn is useful for the task at hand that we train the network for, which is different if we apply separately a graph representation learning and a machine learning approach, because then the representation might not be good for the task that we want. And then obviously this can also be applied to very large data sets, because now we can make full use of GPU-based optimization or backpropagation implementations. And I always like this comparison because I like astronomy as well. This one of the more recent GPU architectures has 40 teraflops, so that's actually 40 billion floating point operations per second. So if you think about the distance from Earth to Alpha Centauri, the closest star, which is about 40 billion kilometers. That means if we would have one floating point operation per kilometer, we would travel that in 1 second. So it's really astronomical, the speed of these hardware architectures. All right. So now, with all of this in place, we can now, as I said, learn useful graph representations. And here is a little example that shows that. So I have created a graph here that has clearly 2 clusters. And I assigned different features to half of the nodes in each cluster. And there's always just a binary number, the feature 0 to that half, and to that half, feature 1 to the other half. And if you now train a graph neural network with this data, we get this representation of the nodes in a 2-dimensional space. And you see that the nodes in the different colors are nicely separated. And you also see that the graph neural network automatically learned that this data has basically 2 dimensions. The one dimension is the node features, and the other dimension is the graph topology, like split into 2 clusters and split into 2 different values of the features. All right. So now, how can we understand what these kind of graph neural networks can fundamentally distinguish in terms of network topology? Also here, a little crash course, how we can use the concept of graph isomorphism to study this. So this addresses the questions which network topologies are fundamentally distinguishable by a graph neural network. And we can define a concept called graph isomorphism, which says when are 2 graphs identical up to node labeling, essentially. So the idea is that 2 graphs are isomorphic if there exists a bijective mapping between the node sets that preserves all of the edges. So it means the graphs are identical in terms of the topology up to relabeling of the nodes. And this is the basis to study expressive power of neural message passing, for instance, based on the Weisfeiler-Leman color refinement algorithm. So this is an important problem in theoretical computer science. Given 2 graphs, tell me whether they are isomorphic or not. The problem is you don't want to try out all mappings because there's an exponential number of them. So the idea of this algorithm is that you start with identical node features, which we can represent as colors of the nodes. And then we, like in message passing, we iteratively update these features by aggregating the features or colors in the neighborhood. And then whenever we encounter a new unique combination of these features, we assign a new color. For instance, if that node has a red neighbor and another red neighbor, this aggregation, which is red plus red, we can then represent as blue. So that means after 1 round of this algorithm, we would recolor the nodes in this case, in this sense. And then we can repeat that. And we repeat this until no new features are assigned, and this kind of dynamical system basically stabilizes. And then when this is finished, then we can check whether the color profiles of the 2 graphs are identical. If they're identical, then it's possible that this is isomorphic. It doesn't have to be. But if they're not identical, then we know that they are not isomorphic. So this is a one-sided heuristic that we can use to test isomorphism. Okay, so that means, and then based on the colors, we can just assign the labels, and we have found that they are isomorphic or not. And why is this interesting for GNNs? Well, there has been a relatively recent work that has showed that a properly parameterized graph neural network using neural message passing cannot be more powerful than this Weisfeiler-Leman algorithm. So that means it can fundamentally not distinguish graphs better than this algorithm, isomorphic, non-isomorphic graphs better. Okay, so this is one approach how we can understand which topological features are distinguishable by GNN or not. All right, so this is the crash course for GNN and expressivity. And now let's actually move on and reconsider this idea of using network models of complex systems. Well, this is actually nice. We can have all kinds of applications of this, of machine learning, of graph neural networks, in terms of predicting, controlling dynamical processes, finding communities, link prediction, assigning labels to nodes or links, for instance, to automatically infer labels in knowledge graphs, and so on and so forth. But the problem is that we often have data where we not only have the topology, but we also have time information. So that means we have information on when and in which temporal order interactions occurred. And well, this is already something that I talked 8 years ago about, when we were actually at the very beginning of this research. but already at this time we had done some works, more theoretical works, that show how this time dimension can invalidate network models of systems, and that this actually limits applications of network science and also graph learning whenever we have time series data on temporal networks. Okay, so why is this the case? Well, it's actually interesting because it has to do with a fundamental property of time, that time is directed, so there's an error of time. And this gives rise in temporal networks to something that we call time-respecting paths, which are fundamentally different from normal path in a graph, in the sense that we not only have to have sequences of edges that are consecutive, but they also have to have timestamps that are basically monotonically ordered. So here's an example of a temporal graph in this time-unfolded representation from top to bottom, and that would be the static representation where we also just count the number of edges. And here we have a path from A via B to C, so that means there is a way how node A can indirectly influence C via node B. So that means in a temporal graph, an edge sequence is a time-respecting path if we have this ascending ordering of the timestamps. So this is the case here. So the interaction from AB to BC, from AB happens before the interaction from B to C. So that means there is a path that follows the arrow of time. What we often also want to consider is some maximum difference between these interactions, because if there's 5 years between these interactions, we may not want to consider this a path of influence, right? So that means we can cut this off by some maximum waiting time delta, where we say it not only has to be ordered, but the difference between the timestamps has also to be smaller or equal than this delta. Okay, so this is an example where we have a time-respecting path from A, Y, B to C for a value of delta equals 1 in this example. So the problem with temporal networks is that without changing the topology or the frequency of these interactions, just by changing the order in which they occur, we can actually break these time-respecting paths. Like in this case, you would think that there is a path from A via B to C based on a static topology, because there's an edge AB and an edge BC. But if you look at the temporal sequence, you see that actually BC happens before AB, so that means there is no way how A can indirectly influence C without violating the arrow of time. And that can give rise to all kinds of interesting effects where the actual, what we call causal topology of the temporal graph can be very different from the topology of the static time aggregated graph. Okay, so and with causal topology, we mean the topology of who can influence whom directly and indirectly via time-respecting path that respects this arrow of time. So causal in the sense that we say, that's always something I would like to emphasize because there is a misinterpretation potential there. Causal in the sense that the existence of a time-respecting path is a necessary condition for causality, not necessarily a sufficient condition, right? You can have this ordering from AB and then BC without having a causal interaction, but you cannot have a causal interaction without that ordering, because then there is no way for the influence to propagate. All right, so this is interesting because it comes from this kind of one-way property of time that doesn't exist in space or also not in graph topology per se. All right, so now the question is, how can we apply GNNs to temporal networks? Well, a naive thing that we can do is we could just take the time aggregated static representation and just apply the GNN to this. And well, it should be clear that this doesn't work really. And here's an example where it doesn't work that I will also use as a running example to show when it works. So this is a temporal graph, which we have constructed synthetically to have a specific pattern. So you see, I have colored the nodes in 3 colors, red, green, and blue. And there doesn't seem to be a pattern at first glance, but I can tell you that we have structured the temporal ordering of the interactions such that there's more time-respecting path between nodes of the same color than they are between nodes of different colors. So it means there's a pattern in the sense that there's temporal communities in the graph that are not visible in the static topology. And also the activation frequencies are all equal. And also the timestamps can actually be shuffled except for this ordering that is preserved. Okay, so if we now apply a GNN just to this static time aggregated representation, because there's no pattern in topology or the weight, we just get a representation that doesn't show this cluster structure. The only thing that we see here is that the nodes have different degrees, and that is how they are kind of sorted in this representation. So it means this representation is insensitive to time. Now, how could we fix this by using what we call temporal GNNs? Well, a common approach is that we split these timestamped edges into sequences of batches, where every batch typically has the same size. And the idea is that all of the edges in one batch we would like to process in parallel on the GPU, and then we process the batches sequentially. So that's a frequent approach to apply GNNs to temporal data. So the problem is that then if we just apply neural message passing and also process all of the batches in parallel within all of the edges within a batch in parallel, is that we do not necessarily preserve information on the temporal ordering of the edges within a batch, even though we consider the sequence of the batches. So that means in that sense, we are not considering the causality structure of the data. So it means we don't get a representation that would actually represent this cluster structure in the data. So a lot of these batch-based message passing approaches thus also neglect the error of time. And that means what we are really interested in is to develop temporal GNNs that explicitly consider time-respecting path and the causal topology so that we can capture this pattern. The other problem in studying many of these temporal GNNs that it's also not easy to say what they can actually express based on the definition. So that's another thing that we are interested in, to define a temporal GNN where we have a clear view on how expressive they are with respect to these temporal patterns. Okay, and in order to do this, we can take a step back and we can have a look at different graph models for temporal networks. The first one we have already seen, it's just a time aggregated graph. So that means we collapse time in a static representation, and what we could do is we could just count interactions and introduce weight parameters or weight features to the edges. And we could possibly do this in a sliding window, for instance, per batch. So this has a couple of positive and negative characteristics. The first one is it's very compact because we just have a number of edges that is much smaller than the number of timestamp edges that we have in our data. It can also be the basis to apply standard network science and graph learning techniques. We can just run a GNN on this. We can just calculate centrality measures, representation learning techniques, and so on. So that's a plus. But the negative is obviously that it is insensitive to the error of time. You see that these two different sequences that have different causal structure, they are collapsed onto the same static representation. And what you can actually say is that that's actually a paper from a long time ago. You can see them actually as a maximum entropy model for time-respecting path in a temporal network under the assumption that all of the edges occur independently based on the frequency that we capture in the weights. So it means there's no assumption of temporal correlations. And that leads to a loss of information on the causal topology, which, by the way, we can also measure based on some entropy measures. And also what we could show in some previous works is that this also gives rise to wrong statements about processes like, for instance, Laplacian diffusion, but also controllability, synchronization, and so on. And this is obviously a problem because GNNs are essentially doing a diffusion of the features. And so that means we should consider how the diffusion process actually works in a temporal network based on the time-respecting path rather than just a static topology. Okay, so how could we fix this in a different representation? Well, the other extreme is that we could just use a representation that preserves all of the time information and turns it into a graph that gives direct access to the time-respecting path structure. And for instance, we could consider these time-unfolded directed acyclic graphs. The idea is that we can just orient the edges in this way along the time axis. So it means we get a directed acyclic graph where every link here is a timestamped edge, and then we can directly see the time-respecting path. And the directedness of the arrows here, of the edges, comes from the directedness of time. So in this way, we force the time-respecting path to always point in the direction of the arrow of time. So it means we make timestamped edges always directed. Even if we have an undirected timestamped edge from V to W, we would actually direct this or change it to two directed edges from node V at time t to node W at t+1, and from node W at time t to node V at time t+1. So that is how we get the directionality from the arrow of time. So again, some characteristics. Well, at first glance, this is a lossless representation of the time-respecting path structure. I should say, at least if we have a delta parameter of 1, because otherwise it gets a bit more complicated. And we can see the weighted time aggregated graph also as some kind of an ensemble average that is compatible with all time-unfolded DAGs that represent different causal topologies that are in line with the same time aggregated graph. So this is actually kind of cool because we can generalize the statistical ensemble approach from statistical physics of networks, so to speak, also to temporal graphs by looking at all static representations that are in line with these edge frequencies. The problem is it is not compact because now we have a number of nodes here that is equivalent to the number of edges with timestamps. And the number of edges is also proportional to the number of timestamped edges. So that means these graphs are extremely huge. So it means if we have 1 million timestamped edges, then that is the size of our graph. And also, it's not easy to directly apply standard network analysis in graph learning because now the nodes are not nodes anymore because the nodes are node time events, and we would have to somehow aggregate them to nodes again, which is not so easy. And there's another complication. If we have maximum waiting times for the time-respecting path and not just one, let's say we would like to model time-respecting path with a time gap of maximum 3. So the way we could do it is we could include this memory here in the edges between the time node events. But the problem that we have then is that if we have multiple paths, we are mixing them, and then we would actually paths that are actually violating this constraint. So it means we have to spend additional effort. For instance, we could have labeled edges here. That means we further have to duplicate edges, or we have a representation where we have multiple edges to future nodes, so that quickly gets out of hand. So bottom line, this is not a very good representation to study temporal GNNs and expressivity. So another approach that we have taken here is that we consider what is called directed acyclic event graphs. And that is not an invention by us. This has been proposed by some other people in network science, for instance, Jari Sahamäki. The idea is that we consider a static graph representation of a temporal network where we say the node set is actually the set of time-stamped edges. So we make kind of a line graph transformation. And we also have time-stamped edge events. So it means this node would say that there was an edge from A to B at time t equals 2. What we can now do is we can add edges to this directed acyclic event graphs between two events whenever they contribute to a time-respecting path. So that means, first of all, the second node here has to correspond to the first node here, and the timestamps have to differ. The difference between the timestamps has to be smaller or equal than delta, and they have to be correctly ordered in time. What we get then is that we have the property that every path with length k in this event graph is actually a time-respecting path with length k plus 1 in the temporal network, and we have a full lossless representation of the causal topology. So that preserves all information on the temporal network. And this has been proposed, for instance, in these two papers that we were not involved in. Okay, so the downside of this is that, again, it's not compact because we have as many nodes as we have time-stamped edges, and even worse, we have as many edges as we have time-respecting path of length 2, which can be in the order of the square of the time-stamped edges in the worst case if you have a large delta. And also, we don't have a direct representation of the nodes in the temporal network because now our nodes have become edges, right? So what we are considering in the first step in our work is a change of, yeah, sure.
So then in their representation, if A sends a message to B at time 10, then there would be another node added there.
Yes,
right?
exactly.
A to
yeah.
B, but that's a T to 10.
Exactly. Yeah, I should have made an example where this appears twice to make this clear. Yeah, yeah, exactly. We will get rid of this probably later.
Fantastic.
Yeah.
I don't like it.
Yes, exactly. But it's good conceptually because it's a lossless representation that allows us to study the structure. So the first step that we took is we defined something which we call an augmented event graph. So it's actually a directed acyclic event graph that we are augmenting by first order nodes. And what we are doing is we are adding essentially edges from the source nodes to the edges. So that means this is an edge that originates in A. So we create a link from A to this edge and to the target. So this is a path, edge that ends in B. So we actually link to B. So what this adds is we have now still the directed acyclic graph property if we do not allow these temporal nodes, so the ABCD nodes, to occur as internal nodes in the path, we only allow them to occur as the starting or the end node. And then the directed acyclic graph property is actually preserved. And we can consider label-restricted path with length k that correspond exactly to time-respecting path with length k minus 1 in the temporal network. So that means there's still a lossless representation. And we have a representation of the first order nodes that we can use to aggregate representations in terms, for instance, of message passing. Problem is, it is still not compact, right? Because we still have as many edges as we have events.
And here you still keep the edge from E to B to B to B, right?
Yes.
The edge that connects.
So it means it's even larger than before.
Right.
Yeah. Okay. So now, how does this help us to understand expressivity of temporal GNNs and to define a new message passing that respects the causal topology? The idea is that we would like to go the same route as using graph isomorphism for the expressivity of GNNs, but extending it to a notion of temporal graph isomorphism that captures exactly what we are interested in. So it means we would like to generalize this definition to investigate the expressive power of temporal GNNs. So this is again the definition of static isomorphism. And first of all, some observations on existing generalizations of temporal graph isomorphism. Many of them are based on static isomorphism, but applied to a sequence of time aggregated static graphs, where you can say, okay, then two temporal graphs are isomorphic if all of these time windows statically are isomorphic. But that again does not respect the error of time, because the ordering within such a time window could be different. So it means we have a different time respecting path structure which would not be captured. Or what we could do is we could just apply this to an edge labeled static graph. So it means every time-stamped edge is preserved in this graph, and then there has to be a mapping. That has a problem that it actually preserves too much information, because we actually don't care whether an edge occurs exactly at time 15. We are only interested in the path structures that result from that. So that means this is too loose and this is too strict. And another observation is, if you think about static isomorphism, it's a mapping that preserves the edges. Well, it's also a mapping that preserves all of the path. And this is because in a static graph, edges transitively expand into paths. So that means that doesn't have to be specifically defined. The problem with these definitions of temporal isomorphism is that they don't explicitly enforce that also the time respecting paths are preserved. And that is the idea for our generalization. We call this a time respecting path isomorphism. We say that two temporal networks are time respecting path isomorphic if there exists a bijective mapping between the node sets, such that this mapping preserves not only all of the edges, but also all of the time respecting path. At this point, we don't care about the timestamps. As long as the time respecting paths are the same, then we consider them isomorphic. So that means the causal structure in terms of who can influence whom via whom has to be identical between the temporal networks. And I would argue that this is a natural generalization of static isomorphism to temporal graphs, because it preserves edges and path. Okay, so one problem with this is, how do we calculate it? Because it would be very complicated, right? So it would be good if you could just reduce it to a static isomorphism. And this is what we do in this paper, because we can show that this is identical to a static isomorphism on the augmented event graph now. So this is actually the theorem in the paper for two temporal networks G1 and G2 with corresponding augmented event graphs. The following statements are equivalent. G1 and G2 are time-respecting path isomorphic, and the corresponding augmented event graphs are actually static isomorphic. So it means we can just reduce this more complicated problem of temporal isomorphism to static isomorphism on a larger graph. Okay, and this is shown here, where we have two different temporal networks. They are time-respecting path isomorphic. These are the corresponding augmented event graphs, and this is the coloring that maps basically the events and the nodes to each other.
So you're basically just doing isomorphism for bipartite graphs.
Yeah, and that also means that we can just apply a labeled and directed version of the Weisfeiler-Leman algorithm to heuristically test for temporal isomorphism, because it's just a static isomorphism on a labeled and directed graph. So we need the labels because of this restriction that the internal nodes should not be in path, and we need the directedness because we fundamentally have directed edges because the error of time makes them directed, right? And what is also nice is that this is now the basis to define a temporal GNN based on the augmented event graph that has a known expressive power because it will be exactly as powerful as the Weisfeiler-Leman algorithm applied to this augmented event graph. And this is basically what we are doing in this paper, which was led by Franziska Heeg, my PhD student. Okay, so we call this augmented event graph neural network. I should say it's not a very practical approach, maybe, because it's a huge representation, but it's good to study what fundamentally can be captured in terms of the temporal patterns and will be a stepping stone for something else afterwards. Okay, so the idea to apply this VL algorithm suggests that we can then actually just apply neural message passing to the directed graph, which is the augmented event graph. So that means we're just applying this directed GNN that was proposed here in 2023 by Rossi et al. To the augmented event graphs. And we call this augmented event graph neural network. And this generates node and graph level embeddings that now allow to distinguish temporal networks based on their causal topology. So it means the temporal GNN will say that two temporal graphs are different whenever their causal structure is different, and will say they are identical if they are just basically different node labels and different time labels, but the structure of the time respecting path will be the same. We also experimentally evaluate this, that this actually works, and we compare it to different approaches. For instance, we could just use the labeled graph, labeled static graph, where we preserve all of the timestamp labels. So that means we give full information to a GNN, and then we run a graph intention network. And so let me explain the first experiment here. We have generated pairs of synthetic temporal networks, which are generated by parameters sigma 1 and sigma 2, the two different networks. And the parameters are chosen such that the causal topologies differ whenever the absolute value of these parameters is actually different. So it means what we should see, this is actually the accuracy of the different pairs of the values. Whenever those are different, so that means off diagonal, we should see high accuracy. And that is something that the graph intention network cannot do, even though it has full information in terms of the timestamps, because it just doesn't know what these timestamps mean and that they need to be ordered in time to contribute to a time respecting path. And so our approach basically can distinguish them whenever they are different, right? And whenever they are the same, they are isomorphic, and then it should not distinguish them. That is what we would expect. Okay, the second experiment we did with empirical data, and we compared it to an actual temporal GNN, which is a state-of-the-art model, TGN architecture. And the idea is that we take an empirical temporal network, and then we create a shuffled version that preserves the timestamps, that preserves the weights of the edges, that preserves the topology, but that selectively destroys time-respecting path and will lead to a different causal topology. And then the question is, can the model distinguish that? And we see again that that actually works with relatively high accuracy. The gut static with time labels cannot do it at all. And TGN is better than that, but we are still better in most cases than the TGN architecture. There's one outlier where actually TGN can also do that. So there seem to be other patterns that TGN can pick up that, that make them basically different.
Do you have an explanation for why it's actually a 1? I mean, so what's special about the S in the actual?
Yeah, that actually is something where we have seen before that there's very strong temporal correlation. So that is so SP means social patterns. Okay. That is the hospital data, and we have different classes of the nodes: nurses, doctor, and administrative stuff. And apparently there's very specific sequences in which, and also patients, in which they are basically interacting. And if we destroy that, that seems to be perfectly predictable that this is the shuffled version in this case. Yeah.
And then for the ants one, where TGN does better, is it because there's more randomness in the times, or?
Ants is a filming of a ant colony with some coding of an interaction whenever two ants rub their antenna to exchange pheromones. So I don't know actually what is the reason for this. And so that definitely requires further investigation. Okay, so now pros and cons of this approach. First of all, we can distinguish with this temporal graphs with different causal topologies. It also in some cases outperforms state-of-the-art temporal GNN, TGN, and we have some analytical understanding what it actually captures based on the Weisfeiler-Leman algorithm and the corresponding neural message passing that we have here. But again, that's not a good approach to apply in practice, because an augmented event graph is not compact. That means it's a huge graph. That also means that the message passing will have a huge number of parameters, and we have a high computational complexity in training and inference, and we would also need large amounts of data. These data sets were still small enough so that we could actually do it. And I should also say that we used here already a compressed version that we talk about in the paper. I will not talk about this here because I would directly come to the next step.
For these data sets, did you have node features, or did you just assign all ones?
We just defined I don't know.
Just on the structure.
Just on the structure. Yeah. No. I don't know whether we used one-hot encoding or random node features. I have to check again. Yeah. Okay. So again, taking a step back and taking a more philosophical approach, the question is now, what makes a good model, right? Because the good thing about the augmented event graph is that it preserves all information in a temporal network. So that's like a very, very detailed map that might not be so useful in practice, like this map of Boston, right? On the other hand, the time aggregated network, for instance, is a nice, very compact model that reduces the data to its absolute bare minimum, just the topology and the frequency. But this would be corresponding to a model that is too simple, right? So that means we don't actually capture the relevant information that allows us to navigate the space, like this map of Boston. So that would be a parsimonious model, but not a good model. So the truth lies in between, that we want to have a model that simplifies, but that still captures the relevant patterns. So that means something that is actually good to actually navigate and to do something in practice. And this gives rise to the next representation that we have used in previous works, but not for temporal graph learning, which we call higher order de Bruijn graph models of time-respecting path. What is the idea? Well, the event graph that we have seen, you could say, is a higher order graph model that captures time-respecting path of length k equals 2. Higher order because the timestamped edges become nodes and the edges become paths. The idea that we could have is we just aggregate edges that only differ in their timestamps. So like what you said, if AB appears multiple times, why should we represent it multiple times? We could just aggregate that and then keep the frequency of the time-respecting path of a given length k. So that is the general idea. Or you could also say it's just a generalization of a time-aggregated graph, where the time-aggregated graph that we usually use preserves time-respecting path of length 1, which are just time-stamped edges. And we make a line graph transformation where we replace all of the edges by new nodes, but without the timestamps. And then we have a space how we can represent the statistics of time-respecting path of length 2 in such a second-order model. And we call this a second-order de Bruijn graph model, because that is a de Bruijn graph which is pruned to not contain even the edges that do not contribute to a path based on the first-order topology. But it's still a de Bruijn graph, which is often used for sequence modeling. So obviously we could repeat this. So that means we can make another line graph, and then we would have ABC connects to BCD, and we could capture time-respecting path of length 3, and so on and so forth. So some characteristics of this. So this is a lossless representation of time-respecting path of length k, but it's a compact, but a lossy model for path of length larger than k, because now we are again assuming that we have transitivity, right, which we might not have. But at least we capture information of one correlation length, and we could combine multiple of those to capture multiple correlation length. And it's also more compact because we do not have to represent every timestamp edge with a separate node, because we are aggregating. And this is also something which in previous works we have shown we can use to define higher order Laplacians, graph Laplacians, which we can then use to study diffusion processes in temporal networks. And as we will see, we can also use to define a temporal GCN. How does this? Yeah.
Slide. So not this one, the other one. So just so I understand that A, B, and then I have the arrow to BC. It means that A and B talk to each other twice before B and C.
I should have explained this because it's here, but I didn't mention it. So exactly, that means there's a time-respecting path from A, Y, B to C that appears 2 times in the data, and this is actually the one that is colored here in red.
Oh, I see.
So on the right side, the edges appear, it's the same edges that appear with the same frequencies, but with different temporal orderings. So it's shuffled. And you see that that is reflected in a different second order topology, because now this ordering A, B, and then B, C never occurs, because here it's the opposite way. And that is reflected by the fact that there is no such edge, which means this captures that there's no way how A can influence C via B in that sequence, right? So there is no such path of that length. So this is nice because it's still a compact model, but you see it is sensitive to the temporal ordering of the edges when the first order aggregate network is not. So we capture some of the causality. And this is the idea to use this for neural message passing, because by this we force the messages that are exchanged onto time-respecting paths so they can possibly capture these patterns in the data. And we define this along the line of a GCN. So that means basically the same message passing dynamics. We have some learnable weights for a given order K now, and we just make a neighbor aggregation. We also make some symmetric degree normalization, just like in GCN. So that means what we do is we essentially do a Laplacian diffusion of the features that respects the time-respecting path, because it has to follow this topology. So if we see it as a neural architecture, this is how it would look. So it means the message passing architecture is given now by the time-respecting path. And we are passing them here from right to left. This is the direction of the arrow of time. Okay, then we can also put some input features. So either we have some input features for the edges, which we can use, or we could just, again, use one-hot encoding if we don't have them. So yeah, like in standard GCN. There's one problem, though, because if we would just do this message passing, we would capture the second order topology of time-respecting path, but we would actually neglect the graph topology, right? Because that is not contained here, or it is only implicitly contained in which nodes are connected here. So what we need on top of that is a first order message passing. So it means we just use the standard GCN approach and add the message passing rule, and then we combine the embeddings that are generated by first and higher order. And we can also combine multiple orders at the same time. So the full architecture then looks like this. Higher order message passing here from right to left, first order message passing from left to right. And now the question is, how do we aggregate these representations? And this is the same idea like in augmented event graphs. So if we have a path here that ends in A, we would like to aggregate this to the representation of A, because that's where the path ends. So it means we make some bipart type projection, where we have here first order nodes, a direct mapping here, and here a mapping to the target node. And this is how we aggregate the representations. And this is another projection layer that we add in the neural architecture. Okay. And then we get a representation of the first order nodes that not only captures information from the topology, but also from the causal topology because of that representation. And we can also tune the correlation length by setting the order K of that representation. And then, just like in standard GCN, we could add dense feed-forward layers if we do some specific classification tasks. So we call this, by the way, dbGNN. It's a De Bruijn graph neural network. Okay, we can also experimentally evaluate this. First of all, the example that I gave. Now we would like to see those clusters in embedding space, and I can just give away we see them. This is the embedding that is generated by dbGNN. So we nicely see that there's these temporal clusters that are not visible in the topology, and it learns this. And this also extends to empirical data. So this is the synthetic one, but then there's actually some real temporal networks where we also have ground truth classes that we would like to predict. And we compare this to different other embedding and GNN approaches. And we see that this approach actually leads to a substantial increase in classification performance, and also for more data here. So we observe performance gains up to 18%. And this is still so compact that we can actually train it on large data, obviously depending on the correlation length that we would like to capture. Okay, now I'm out of time. That's why I'm closing. Thanks a lot. If you're interested, you can also play with this. So we have this library out that implements that stuff. There's also a lot of tutorials with some sample data where you can try this. It also allows you to construct these directed acyclic event graphs from the data, and it's based on Torch. So that means it's also using GPUs to do these transformations, and it works internally completely on tensors. But it still has the more network sciencey front end, in the sense that you can ask for successors of nodes, that you calculate centralities, and so on and so forth. So it's a good combination also of the torch world, where everything is a tensor, and the more network science libraries, where we would like to also make graph traversals, for instance. Yeah, and if you're interested in more technical details, there's also the pointers to the relevant papers. Thanks a lot.
This is awesome. So for some of the hospital data set where there's the RFID, there's 3 people together that
I think it
show up as a hyper edge.
No, I think it doesn't.
That hyper deployment.
I think it's not RFID. Is it RFID? I think it's IR sensors, batches basically that register pairwise, yeah, face to face.
Other like software-based ones.
Yeah.
There's the potential.
Reality mining, for instance, one.
Edge transitions.
Mm-hmm.
It seems like everything's flexible enough to accommodate.
That could be an approach, yeah. It would make the model more large, because then you also have the different combinations, and you have to consider what kind of interactions you consider. But in principle, you could also have sequences of group interactions that you could model in a similar approach, potentially. Not that we would have considered it. That's also pairwise, but I guess the socio patterns could be reduced and a hypergraph could be constructed from it, because it's anyway fixed sampling intervals. So if you find clicks there, you could say these are actually higher order interactions. Yeah.
The other just the point about that middle layer in the run graph on the left.
Mm-hmm.
If you have higher than second order, you just smush another.
Yeah.
So, given the operations issue, distributed complete temporal stuff, lines in geometry appears all the time. It's the causal structure, most fundamental thing,
Mm-hmm.
objects. Not so much in this temporal network. So basically, the causal structure here would be, for example, the future light cone of node
Exactly.
at time t with the set of all the nodes reachable in the future.
Exactly. With some cutoff potentially. Yeah.
Cutoff at time.
Yeah.
So, but the future, that's usually
Mhm.
basically looking for the, but it doesn't appear, for example, in your case. Can you give a high level why?
So this is a very interesting question, and there would be, I guess, a lot that could be said to this. I mean, it does implicitly appear here. So the light cone property would be this smaller equal property of time, right? And this delta could be infinity. In that case, you really have your light cone that extends into infinity. We typically also consider some cutoff, and we say it has to appear within a certain time window, because we're not interested in a path that has a 5-year gap in between, right? But it's not fundamental to the framework. So, yeah, I mean, first of all, does this answer that question?
Well, somewhat. And
Yeah.
you said that, for example, this representation is not good for you. I forgot why.
Because it's not compact in order to learn on it, right? So the problem is that in terms of message passing, if you would just run a message passing here and we have all of our learnable parameters, if you have 1 billion edges, you have 1 billion nodes, right? So we would like to compress it in a sense. Yeah. And that is what the De Bruijn graph does. So it tries to do the same like a time aggregated graph, like aggregating things that just differ in timestamps, but then it still preserves the temporal ordering of causal structure to a certain degree, right? What you could say is this is, or let's go back to this representation. This would be lossless if your k is infinite, right? Because then you can have infinite sequences in which you encode that it was exactly that order, but then you would be back to the old complexity because then you have to consider all paths of any length in your representation. So we want to have a balance. Exactly, it's a coarsening. And I should say, I didn't mention this here. I think that's what I talked about 8 years ago. There's ways how we can learn that from the data. So essentially, it's like a Markov order detection problem. You would like to infer what is the correlation length that we need to model that is still justified by the strength of the patterns in the data. And that's what we can do. So there's two different approaches that we have published, a Bayesian one and a non-Bayesian one, where we can say, okay, what is the maximum order of the representation that is justified, given the path that we observe, right? And that depends on the size of the graph, on the amount of data that you have. So it means there's also a way that we can choose this representation that we should use for message passing from the data. We don't have to guess it, which is a benefit.
So since you're not doing a streaming approach, I have
Yeah.
all of my data, right? So I know all the times now. Why don't I just do the De Bruijn graph, and then for every node, which is an age A to B, just have a feature vector in terms of what times they talk to each other. And the first one, the meaning of the first feature is that that was the first interaction they had. And so that would be consistent across all of the nodes here.
So the idea would be, instead of aggregating 2 or 3, you would have a vector of the timestamps at which they
for every node, right? Because you're not doing streaming, so you know the exact time, right? Like how many, right? So for every node, you have a feature vector, and the size of it would be all the possible times. And then, and of course, the feature vectors could be sparse. You can pack them, whatever, and then you won't have any of this, and you won't have to add the other tack on thing. You just do this. It's you have your feature vectors. These graph neural networks are very good with dealing with node features, right? And every entry in the node feature will be consistent across the nodes, which is important, right?
Could you still compute the time respecting path from that easily?
Time respected well, I don't care about computing the time respected paths. I know that the information is encoded in the graph representation. So all of your machinery will still see that information. It's just in terms of the nodes. And I guess I could extract the path from that if I wish to. That would be more computationally. Right.
No, we should talk about
but
it
you're
now.
not extracting the path anyway. Like, you're not doing this to extract the path. You just want that path information in the network itself.
Exactly. So the motivation of this is that we can apply. I mean, I could talk longer about this. You see that it is specific in a sense that it overlaps always in exactly one node on a path. So AB and BD overlap in node B. And that's a general property of a De Bruijn graph model of order K, that they overlap in K-1. So it means that every step that I take expands the path by exactly one step.
No, I understand.
Yeah.
No, that would be just fine. It's just that the time element are stored in the node.
I'm not saying that this invalidates it. I just wanted to explain the rationale behind it, because that has the benefit that we can still apply the whole graph machinery. So you can interpret matrix representation of this and calculate matrix powers. You can calculate eigenvectors of this, and it makes sense. Yeah.
I don't like node features, but I was trying to channel somebody who works at Pinterest that has all this information, and like, look, this is just time information. I can have the network be smaller and just have node features that take the time into account. Now they have the streaming model. Here you don't have the streaming model, because you're getting all of your data all at once for hospital A, right? Because then it would be different, because your node features will grow.
Yeah, and also what is special here is that, that's maybe also something to emphasize. What is special is that we have a temporal graph, but we get a static representation of the nodes, but that static representation contains temporal information, right? So because that is not an evolving representation. That's sometimes something we really have to emphasize with the temporal GNN community, because many of the models do differently, right? Yeah.
All right, so we are past the hour. Do you guys online have any questions? I didn't say that with a lot of conviction. I didn't get any, so I don't get